Welcome back. We are looking at Khan Academy. We are in Algebra 1 and we're in the unit Quadratic Functions and Equations. This is second skill, interpret a quadratic graph. So they give us a contextual problem and a graph of a parabola that is a graph of a quadratic function. And so we're asked some questions about what these things mean in the context of problems, which is why it's important to learn this stuff in the end, is because it's useful to model things that actually happen in the world. So let's read this. Simon has a certain length of fencing to enclose a rectangular area. The function a models the rectangle's area in square meters as a function of its width in meters. Okay, so pause right there. The context is that he's got fencing material and he's going to make a rectangular enclosure. Okay, so we've got a rectangle and A models the area of the rectangle. So the area equals something. We know what the area of a rectangle is. It's length times width like that, right? So if the length and the width were given as binomials, something like x plus 5 and x minus 2, if these were the side lengths of that, then we would have a function a that equal x minus 2 times x plus 5. And that could be written, if we expand that with the distributive property, that could be x times x is x squared, x times 5 is 5x, minus 2x is 3x, minus 2 times 5 is negative 10. So we get a function that's a quadratic. This is interesting because we have a rectangular area, but the area is modeled by a parabola. Let's think about what that means. Here's our parabola. This is a parabola, not necessarily for the function I came up with, but it's like that. It's going to be a quadratic function. And the function value, that is the f of x value, the y value, is telling us what the area is. Okay? So that means that over here, when the area is 0, that's because one of the two sides of our rectangle, one of these two sides had to equal 0. Fair enough. If the side of your rectangle equals 0, you've got no area. And at another point, when x causes this side to be 0, you're going to also have an area of 0. If either of the dimensions of my rectangle are 0, I no longer have a rectangle, which means I no longer have an area. Okay. It also shows us that as we change the lengths of those sides, at some point we're going to maximize the area. We're going to maximize the area. At some point, if we do the right dimensions, we will get the best possible, or the most area, if that's what we say is the best. If we want to get the most area for the fencing material we have, that would happen when x is 10, in this case, in the function that they gave us. Okay? So, which of these statements are true? Now they're going to ask us some questions. So essentially this is true or false for each of these statements. Greater width relates to greater area as long as the width is less than 10 meters, okay? The width, here's 10 meters, that was our maximum. If our width is 10 meters, our area is maximized. If we're to the left of that, as long as the width is less than, right? To the left on width being meters, to the left is less than. Greater width relates to greater area, right? If I increase my width from the left side of 10 all the way up until 10, I'm increasing my area. That's true. Let's look at the next one. Greater width relates to greater area as long as the width is more than 10. Well, once I get to 10, I'm at my max, and if I increase the width, this graph shows that my area is decreasing. So that's false. C, to get the greatest area, the width should be 10 meters. Well, that's true. That's when the width is 10, I'm here at the maximum point. I'm at the vertex of this parabola, and that's the greatest area. To get the greatest area, the width should be 20. Well, the width is larger. But apparently, if the width of that rectangle is 20, I don't have enough fencing to make a rectangle anymore. I have no area at all, so that's false. And we are done with that one. Next question. The function g models the number of mosquitoes, in millions of mosquitoes, it must be Minnesota, in a certain area, must be Minnesota, as a function of rainfall in centimeters in that area. More wet, mucky stuff, more mosquitoes, until at some point, you have the best circumstances for breeding mosquitoes. But if you make it really wet, if you become an ocean, you no longer have mosquitoes because the water's moving too much for them to breed and be successful, right? So if it's dry, you don't get mosquitoes. If it's overly wet, you don't get mosquitoes. But somewhere in the middle there, you maximize your mosquitoes. Which of these statements are true? More rainfall relates to more mosquitoes as long as rainfall is less than 2 centimeters. Here's 2 centimeters. Looks like we're increasing until we get to 2, so that's true. More rainfall relates to more mosquitoes as long as rainfall is more than 2 centimeters. That's not true because now we're decreasing. Okay? When there is no rainfall, there are about 1 million mosquitoes. Where's no rainfall up here? Well, rainfall is our x-axis. Rainfall is 0. Mosquitoes are 0 according to this. So that's false. We don't have 1 million mosquitoes. We have no mosquitoes, which is good. When there is no rainfall, there are about 2 million mosquitoes. No. Again, we have 0 millions of mosquitoes when we have 0 centimeters of rainfall. Next problem, Sarah kicked a ball in the air. The function f models the height of the ball in meters as a function of time in seconds after Sarah kicked it. And actually, theoretically, with no other forces like wind or friction or other things acting on the ball would actually follow a parabolic path through as it launches. You've seen that maybe with games like Angry Birds or any of those games that are shooting something at a target, right? So it follows a parabola. Which of these statements are true? So notice, x is modeling time after it's been kicked, and the height of the ball above the ground is the y-axis. So on the x-axis, we are 0 meters above the ground. So the x-axis, in a way, represents the ground as far as its relationship to the y-axis, but it actually represents time moving forward, right? So the ball starts here. This is interesting. The ball doesn't start on the ground. It starts here. She kicks it, right? So it's not on the ground when it starts. It goes up for a while, then it comes down, and eventually it hits the ground. Choose all answers that apply. The ball moved upwards for about 3.5 seconds. Well, let's look. 3.5 seconds is over here. It went up to here, but that's not 3.5 seconds. It came back down. In fact, it hit the ground before you got to 3.5 seconds, so that's false. The ball started moving upward after about 1.75 seconds. No, no, no. It started going up right when she kicked it. The ball hit the ground after about 3.5 seconds. Yes, that's what we saw here. 3.5 seconds. Just before that, it hit the ground. So we'll pick that. The ball hit the ground after about 1.75 seconds. No, 1.75 seconds is pretty close to where the ball reached its maximum height. So this is the only one. And I'll leave the rest to you.